Welcome back to Natural Disasters. For the second week, we will be discussing earthquakes. The questions for homework and discussion for week 2 um, are these 3 questions. And from this week on, our questions for discussion and homework will be essentially the same questions. All we will do is we will change the hazard that we discuss. So the first of the questions is, would you live in an earthquake zone, and what level of risk from earthquakes is acceptable to you? So that's the first question. And you would want to explain your answer to that. The second question is, how would you know if the earthquake risk was assessed accurately? And some people get the notion that the only way you can know is to wait until after an earthquake happens and then look back and see if the risk was assessed properly. That's not going to be helpful to you if you're buying a house or planning to move into an area. So what we really want to look at here is, how do scientists study earthquakes? And if you look at an earthquake risk assessment, what kind of characteristics would you be looking at that would tell you that the assessment was done correctly? So we don't want to wait till after the earthquake. We want to know kind of, was information that we understand about how earthquakes work taken into account when this risk assessment was produced. So how do you know ahead of time if it's a good assessment, if it's something that you should use when you decide to buy a house, purchase insurance, etc.? And then the third question is, what should be done by people, that's individuals, and communities within an earthquake zone to prepare for the hazard and prevent catastrophe? And this is kind of a two-part question. Is there something that people should do? Is there something that communities should do to prepare for the hazard? So the first thing we need to do is discuss earthquake terminology. This diagram is taken from your textbook. It shows the focus of the earthquake, and that is where the rupture movement on the fault plane begins. Once the movement begins, it spreads along the fault, not necessarily radiating out from a central point. It could go in any direction from the focus, but it moves out from the focus, and adjustment along a large portion of the fault takes place. The point on the ground surface directly above the focus is called the epicenter, and this is typically what you see plotted on a map on TV after there's been a big earthquake. And then the surface rupture is simply what occurs if the fault plane rupture makes it to the ground surface. And this does not always happen. Sometimes it happens, sometimes it does not. So sometimes you see surface rupture, sometimes you do not. But the key terms are focus, epicenter, and an understanding that once the earthquake begins, a whole section of the fault will rupture, and it may or may not contact the ground surface. So what causes earthquakes? Our best explanation is what's called the elastic rebound theory. How it works is that if you look on the right-hand side, the two sides of the fault will move. Now the rocks have a certain amount of strength, and so what happens is stress causes what we call strain to build up. And at time 2, you can see the rocks have changed their shape, but the fault itself is locked because it's strong enough to hold that energy. At time 3, we've moved the two sides a little bit more. The energy that built up was enough to overcome the strength of the rocks along the fault, and they rupture, which generates an earthquake. And so that's when you see a section of the fault give way. And then at time 4, we have a new stable situation and movement on either side of the fault continues, and the buildup of stress begins again. The primary cause for this buildup is what we call plate tectonics, and your book has a pretty good explanation of this. But suffice to say that the Earth's surface is made up of large plates that move around and interact, and if you happen to be on a boundary between two of these plates, you're likely to live near a fault or a set of faults. So that's what causes earthquakes, and that's really going to be the basis for our ability to forecast movement along a fault. So how do we measure these things? Well, what you will find in the news typically is a report of the magnitude. There is one number per earthquake. It's related to the amount of energy that's released. And the measurement is described on, originally it was on the Richter scale, and we still do see this because you can get a Richter magnitude very quickly after the earthquake occurs. More commonly now, scientists prefer to use the moment magnitude, and the moment magnitude is related to the amount of movement that has occurred along a fault, and it's also related to and based on the Richter scale. So they're very closely related. The moment magnitude is simply more accurate. The other way that we measure earthquakes is with intensity. And the intensity is what you see in so the intensity is useful because it shows us the impact that an earthquake of a given magnitude will have in an area. And it allows us to study the effects of an earthquake and then look at what caused different amounts of damage in different areas. If you look at the map on the right-hand side, you can see it has a series of zones from that deep red zone, which has an 8 to 9, to the orange, which has a 7, and then the lighter orange is a 6, and so on. And so it looks kind of like a bullseye pattern. Curiously enough, the intensity does not always tell you where the epicenter was. So the epicenter may or may not be where that red dot is. The variations in the rock materials and other factors can determine where the most damage occurs. And so the beauty of the intensity is it helps us understand exactly how seismic waves work and what to expect with future earthquakes. So this is an assessment, again, that's done after the fact, but for a future potential earthquake, they'll use computer models to generate expected intensities, which will help people plan in terms of what kind of insurance do I need, how strong should my building be. So what causes the damage? Well, obviously the motion of the ground is going to determine the damage, but there are other factors as well. For example, the duration of shaking turns out to be a very important factor. The longer the earthquake, of course, the more damage you would expect. The surface rupture. Sometimes this happens. You can see in the lower left-hand corner. Sometimes it does not. It just depends on whether that rupture meets the surface. And obviously, if you have surface rupture, it can cause significant damage to things that are built across the fault. Another factor is poor building design. If you look at the picture in the lower right, you can see in that one small area, some buildings are standing, some have been completely turned into rubble. And a lot of that has to do with the design of buildings. Some other effects that we see, you can see the surface rupture there on the left. You can see building collapse on the lower right. You can see, obviously, people die when buildings collapse. Fires are a common effect of earthquakes. When the buildings collapse and gas lines rupture or fires spill out of people's fireplaces, they can cause buildings to catch on fire. Some secondary effects that we see on the lower right, you can see a landslide. We will discuss landslides later in the semester, but when you shake the ground, you can cause a hill slope to give way, and that can cause a lot of damage. On the lower left, you can see some buildings are intact, but they've tipped over. And this is the result of something called liquefaction. If you shake wet ground, it can turn into liquid, and obviously that would be bad for the foundation of a building. And so in this case, the building just kind of settled down and tipped over when the earth turned into liquid. So what kind of factors are we looking at here? Well, a big factor, as we said, is the amount and duration of shaking. Another very important factor is the water content of the soil, partly because it can result in liquefaction, partly because we see that it has an impact on the amount of shaking. I'm going to skip over most of these, but at the very bottom you'll notice one of our factors is material amplification. And so depending on the materials you have, some materials, loose materials, will tend to move a lot more than really solid hard rock will. And so that's material amplification. So what do we do with all this information? What will you find when you read the book? Well, one of the things you'll see is that we can do some seismic forecasting. We can identify areas at risk and then predict how likely they are to move. And we can also forecast what kind of movement they would expect. So we can use those computer models to do intensity forecasting as well. The trick here for forecasting is to go back to our model of elastic rebound. We can detect how much energy is building up on these faults, and based on that information and what we know about the strength of the rocks and what we know about when they've given way in the past, we can forecast how likely a given section of fault is to rupture in the future. And you can see this is a map for the San Francisco Bay Area. They have an overall forecast of a 62% chance of an earthquake. And you can see they've broken that down for different sections of different faults. So what do you do with this information? Well, the first thing you do is you adapt your structures. You try to build them in such a way that when the ground moves, the structures won't collapse. And that's really a very important thing to do, and we see the effect of not doing that in a place like Nepal, which is a very poor country. They don't have the resources to what we call retrofit or backfit their buildings so that they don't collapse. And so when they had a big earthquake this spring, they had a lot of buildings that were completely destroyed. It's not that they didn't know the earthquakes were likely, it's that they didn't have the resources to fix those buildings to stand up during an earthquake. The other thing they discussed in your book that's really interesting is what's called a warning system. You'll notice it has in the lower left-hand side, they show this warning system. The whole idea here is that when the ground starts to move, the seismic waves move at the speed of sound. You can send a radio wave at the speed of light ahead of the seismic wave, and it can do things like alert the fire department, shut down gas lines, and issue general warnings to people that these seismic waves are on their way and will be there within a few minutes. In Japan, for example, they shut down rail lines, and then that protects the trains from going off the rails. And so that's kind of the basic overview of earthquakes for the week.